Now, implicit differentiation can be used to expand our knowledge of functions, particularly inverse trigonometric functions and logarithmic functions. It can also extend to other functions as well. Let's start with inverse trigonometric functions. We'll get to logarithmic functions later. Recall y is equal to the inverse sine of x means that sine of y will get you x, as long as y is an angle between negative pi over 2 radians and then less than or equal to pi over 2 radians. If you're interested in the domain here of inverse sine of x, I could certainly include that. The domain of the inverse sine of x is the possible trig values. So it has to be between -1 and +1 inclusive. Now, why don't we implicit differentiate to try to get the derivative of the inverse sine of x? Meaning we'll start with this equation and we'll differentiate this with respect to x, knowing that y is actually a function of x. Okay, remember, y here is a function of x. That means we have to apply the chain rule. So if you differentiate sine of y with respect to x, the derivative of the outside function evaluated at the inside function, it's simply going to be cosine of y times the derivative of the inside function, which is the derivative of y with respect to x. Now, our goal is to solve for dy dx. That is simply the secant of y. If you're trying to figure out what is the secant of y, maybe we need to find the cosine of y. So remember, y was a very small angle. I shouldn't say very small, but it has to be less than pi over 2 radians. So we're going to go ahead and draw our triangle scheme. There's your acute angle called y. Sine of y was x. So sine of y is opposite over hypotenuse. So what does cosine of y has to be? What does cosine of y have to be from the Pythagorean theorem? And we are assuming we're in quadrant 1 here, so it will be a positive length. After solving the Pythagorean theorem, you realize you get 1 squared minus x squared, and that is the cosine of y. We could substitute that. So the derivative of y with respect to x is now equal to 1 over the square root of 1 minus x squared. We can't have 0 in the denominator, so that means x has to be between -1 and 1 and non-inclusive. So you can't include 1 here. Cannot include 1. Now, what is y? Let's see. If you're paying close attention, you just got to substitute y back in. Y was the inverse sine of x. So there you go. You now have the derivative of the inverse sine of x function. You even can state the domain. Isn't that beautiful? Just beautiful. We could do a similar technique or similar procedure for the inverse tangent of x. If you're curious about the domain of the inverse tangent, it is actually the set of all real numbers, and we can write it in interval notation. But we're going to go ahead and implicit differentiate this as well and see what happens. Remember to use the chain rule. There it is. It just took place. Now, what is the secant of y? We'll go ahead and use our triangle scheme again. Right triangle scheme. Has to be a right triangle scheme. There's your angle y. We know that the tangent of y is x this time. So opposite over adjacent. There's the tangent of y. We do need the hypotenuse. So after the Pythagorean theorem, we know this is the square root of 1 squared plus x squared. Now, what is the secant of y? Secant of y, remember, is this scheme. It's this ratio. It is actually hypotenuse over adjacent. Oh, we got this. So dy dx, or derivative of y with respect to x, is equal to 1 over this quantity squared. Now, what is y? Back substitute for y. Go back and find y. Y is the inverse tangent of x. And look at that. That is gorgeous. You now have the derivative of the inverse tangent of x. And what is its domain? It's actually all real numbers. You could do similar processes of computations that will get you this following table. You might want to do it for practice on your own. That way you could convince yourself to memorize this table a little bit easier. It does take practice. It does take time. You need to be persistent with many different math problems. And that way you start remembering this left-hand column a lot quicker than this right-hand column. All right, so these are more common functions. We need the inverse sine of x more. We need the inverse cosine of x more. We need the inverse tangent of x more. So really concentrate on getting these correct. And then these are bonus. All right, these are this. If you can get these, that's even better. But notice these first four aren't very difficult to remember. They're actually quite simple. There's a pattern going on. So concentrate on these four here. And, practice memorizing them, practice using them in other problems, and you'll get better and better at calculus.